in the initial value problem, how we solve the partial differential equation is we are given an initial value corresponding to say a certain time t equal to t0 or whatever it is. So yeah, as I said, this should be the time axis and this is the space axis here. And for time t equal to t0 or 0 whatever, we have the initial the value of the function u of x at t0 is provided, as well as u of say some u at x min comma for all time and u at x max for all time. This is provided. These two values are called as the boundary conditions, and this is the initial value. Given this condition, we have to solve the maybe for given at t equal to t0, if the behavior of the function is given, we have to find what will be the function at a later time t. So this is the problem we have to solve, and that's what is our initial value problem. Let us study an initial value problem. For example, let us take the heat equation. Okay, in a simplistic form, I can write the heat equation as del u by del t. So we have some constant k. I am going to remove all those things. We can write in terms of say something like del u by del x square. So this is an example of a initial value problem. So let us try to solve this initial value problem using finite difference method. So what the first thing is, of course, we have to use FTCS scheme. So there is a time derivative, so this will be for forward difference we will use, and the space derivative, of course, this has to be a central difference scheme we have to use. So on the first step is, as we saw earlier, the first step is to discretize our u. So u here, this time the u will be a function of x comma t, and this has to be written as u of ij. Let us write I equal to 0, 1, 2, say up to n, and I corresponds to variable t, and j goes from j goes from 0, 1, 2, 3, say up to m, and this corresponds to variable x. So and this is how we have discretized the function u, and we are given a initial condition, say some u at x comma t0. Let me call it as some say u0 of x. So this is the initial condition, initial values provided, and there are some boundary values, and we have to solve this equation. So the first step is to convert this partial differential equation into a finite difference equation. So in a finite difference equation, so what it is going to become, so when we have used I for the variable t, this is a derivative in t, so and we are using a forward difference, so this is going to be u of I plus 1 j minus u of say I j divided by, okay, I forgot to tell about this interval. For the case of I, we will use this interval as delta t, we will call it as h, and for delta x we call it as k. So this is going to be h, and so here right hand side is going to be a so right hand side is going to be a central difference. So we will write this as, for example, so for time being I am not going to write this. So I am not going to write the I, the index which corresponds to time, rather I will write it as u of, so center difference will be j plus 1, and in the place of I, let us choose, well, I am not going to write it as a star, let us see what it is, minus 2 of u star j, u star j plus u of u star j minus 1 divided by k square. So this is what, and now what should be our star? So this, the choice of star divides the initial value problem into two types. One is when I replace a star as I, This type of problem we call as an explicit scheme. And when the star is replaced as I plus 1, then we call this as an implicit scheme. What is the difference between these two schemes? It's a very it is quite important of which scheme you are going to use, and what is the difference is, suppose when I use the explicit scheme, that means the star, all this star is going to become I. All this star is going to become I. That means when I start with the initial value, say something like, so this is the I where I equal to 0 or something, whatever I do, when I go for the next iteration, that is I plus 1, the way is, if you see this whole equation, only is I plus 1. In the right hand side, all will be I. These are all correspond to the earlier values. So that is, they are known quantities. So only this will be the only unknown quantity. You can take all these terms to the right hand side, and then you can solve for u of ij for the every next grade. We can do that. And on the other hand, when star is equal to I plus 1, that means you are not having this right hand side is again becomes unknown, because we want to find out the value of u at a further time, I plus 1. So these are the points, some grid points we have to find out. So this is going to become an unknown quantity. So this will instead go here. And so eventually what you will see is, we will see it slowly, this eventually again form a matrix equation. You have to solve this matrix equation to find out the behavior of u at the next time grid. That is very important, because in initial value problem we don't reach your final t. Suppose for this is the t you want to find out, you don't jump from here to here directly, rather you divide this time into different grids, and then you keep iteratively slowly reach above the desired time what we want. So first what we start with I equal to 0, that corresponds to this one. Then we calculate for I equal to I plus 1 by using this whatever, choosing a particular choice of star, and then we go for I plus 1 to I plus 2, I plus 3, go for I plus n, which is 0 plus n, I plus 1, I plus whatever, so certain n which corresponds to our time, and that is the solution which is required. This is how an initial value problem is solved. So now let us go in detail about what is this explicit scheme. What we are going to say now is the explicit method. I would call it the method rather than a scheme. Okay, so what we are going to see is the explicit method. What is the equation? In the explicit method, the heat equation, the finite difference approximation of the heat equation is going to become like u of I plus 1, that is I is the corresponds to the time derivative, j minus u of ij divided by h is the interval width that we choose, and the right hand side will be, in the explicit scheme, in the right hand side we are going to write j plus 1, and this will be again I, as I said I, because for implicit will be I plus 1, for explicit star is made as I, so this will be u of j plus 1 I minus 2 times u of ij plus u of ij minus 1 divided by k square. So this is what in an explicit scheme, in explicit method, how this initial value problem is being written. So this is the finite difference approximation for the heat equation, okay, in the explicit method. Fine. So now what am I going to do? Let me take this h here. So and if I write, if I take h here, it's going to become h by k square. If I write p, say some if I use for p is equal to h by k square, So then what we are going to do is this equation is going to become, and so this all i's are all known quantities, because we start from certain I, say I equal to 0, we will find out u of 1, and then after knowing 1 you will go for the u of 2. So I forgot to tell you, this is what I have made the grid points for the initial value problem. This is the initial value here which is given here. So this is the initial value which has been given here, and this is your two boundary conditions. So this is I equal to 0. From here, this is the initial value is known to be, so we will find out for I equal to 1, and knowing this value, then we'll hop to the I equal to 2, and then I equal to 3, keep on doing to ultimately you get a I equal to 1, which corresponds to a certain time t final or what, for which, during which duration you need to find the behavior of the function. So this is what we do it in a initial value problem. So now expressing p as h by k square, and now if you see in this equation I plus 1, when I start with I equal to 0, all this is 0, these all are known quantities because these are the initial values. So only this is an unknown quantity, and we will find out for u1 you will find, u1j you will find, then keep on doing. So if you see here carefully, this u of I plus 1 is a known quantity, all i's are known quantity, and if you represent h by k square as p, then this equation is going to be u of I plus 1 j will be, let me write it bigger. So u of I plus 1 times j will be equal to p times u of I j plus 1 plus 1 minus 2p u of I j plus p of u of I j minus 1. That's something comes from here itself. This one comes from here. So this is the finite difference equation we have to solve, and you can see clearly. So for every I, so for example, if this is the I plus 1, so this is going to connect 3 points of I, that is, so correspondingly I plus 1 points, and this is the j, I plus 1 comma j, for example. This is the point corresponding to I plus 1 comma j. That's what we are going to find here. So this point connects to I, that's a previous point, j plus 1, j, and j minus 1. So that is, this is j plus 1, this is j, and j minus 1. So what happened every point, so when we are trying to solve this, so when I start from a boundary condition, this point is estimated from the 3 points of the earlier grid. Similarly, this point is going to estimate it from the 3 points of the earlier grid. So similarly, this will keep estimated from the 3 points. You keep on doing it. So eventually what happened, you find out all these grid points, and then after finding the grid points, so then go to the next time grid, and then again you use this point is estimated by connecting these 3 points, and this point is getting by connecting these 3 points. So this way you keep on finding out all the points here. So slowly keep progressing up to the end, which corresponds to time tf. This is how in a explicit method an initial value problem is solved. So this is what we call as a So this is what we call as an explicit method. Fine. The problem, the explicit methods are often very unstable. The reason is because every point, every point is anchored up with the earlier point. Okay, and many times what happens, these points doesn't have any dependence upon the earlier points. At every time grid, these points are actually, every points are calculated from the earlier points, and they won't have any direct connection with the points of the same time grid. So this thing will introduce a lot of errors in this explicit scheme. So therefore explicit scheme is always unstable. So if in any of the initial value problem, if you are trying to solve using explicit scheme, then the stability of the solution is very important. There are methods to study the stability of the procedure of the finite difference method which you are using, which I am not going into detail, which I am not going to discuss about it. If you are interested, you can read from the books given in the references below. So rather I will just stop this explicit method here. It is not advisable to use the explicit scheme unless until you have other constraints. Rather one has to use the implicit schemes. They are relatively much stable, and even if the implicit schemes are also, you should require the stability criteria to be checked always. Okay, so and that's one of the important part in a partial differential equation. If you have a differential equation and if you don't check this stability condition while solving this partial different initial value problem, so then that solution can be lead to wrong results, or you can't trust those results. So and that's the reason I said from the beginning, this lectures on partial differential equation is a very preliminary. To get a completeness, you should know, you should also study about the stability, how we are going to confirm the stability of this solutions, what you stability of this procedure, what you are going to what you are implementing. Okay, so now let us go to the next method, that is what we call as a implicit scheme. So what you are going to see now is the implicit scheme, implicit method. So what we had is, what we had is our the heat equation. The finite differential approximation of heat equation is something like u of I plus 1j minus u of ij divided by h is equal to, and this will be u of, so since this is an implicit scheme, if you remember what we did is your star will be replaced by I plus 1, so this is going to be I plus 1 j plus 1 minus 2 of u of I plus 1 j plus u of I plus 1 j minus 1 divided by k square. Again, if I use p is equal to h by k square, this equation will be transformed to u of let us take, okay, yeah, here I want to see the point is u of I plus 1. If you go back to that plot earlier what we saw, the I plus 1, so the I is here, the I is a known quantity which starts on the initial value, I plus 1 is the unknown quantity. So here if you see all these I plus 1s are the unknown quantity, only this is a known quantity. So all the other quantities are known quantities, so we will take all the unknowns in the left hand side and the known quantities in the right hand side. Then this equation is going to become I of j I plus 1 minus, okay, let me write down this equation first properly. So minus u of I of j, and that will be when I take h here, so you can p into u of I plus 1 j plus 1 minus 2 times u of I plus 1 j plus u of I plus 1 j minus 1. And now let me take all these unknown quantities on the left hand side and the known quantities on the right hand side. When you do this jugglery, what you are going to get is minus p times u of I plus 1 j plus 1 plus 2p plus 1 into u of I plus 1 j minus p into u of I plus 1 j minus 1 will be equal to u of I j. So this is what the final the finite difference equation which we wanted to solve. So now if you see, so this is a known quantity, these all are unknown quantities. So what happens here is, if you see back here, in this case it is reverse. The triangle acts exactly reverse. It means every I plus ith point. Okay, so for example here, let me see what happened. I should have, yeah, so okay, let me pull down this figure here. So what happens is, so for example, let us take any ijth point. So let us call this as my I and jth point. So let me call this I comma jth grid point. So this is going to be connected to 3 points of the future grid. That is, so this is u of I plus 1 j that falls here, and this is u of I plus 1 and j plus 1 that falls here, and I plus 1 j minus 1 that falls here. So this is how all this the future points are connected like this. So this basically the triangle will get inverted. So now, and these all are unknown points. These are the unknown points. We have only known points. So the same way earlier we did. So now what you happen is, this is all the initial values. What you get, every point will be connected with the 3 points in the future. So that is like this here. So this point will be connected with this triangle, and then this point will be connected by this triangle, and this point will be connected by this triangle. So you have to keep on. So what eventually we are going to do is, so it is not that you can solve like earlier you can solve one point one by one, we can solve all the points. Now this will give rise to a matrix equation of the form matrix A dot u will be equal to, say, some, I will call it as again as B. So this is the matrix equation which we need to solve, and the solution of this matrix equation, this is important, very important. Unlike your boundary value problem, the solution of the matrix equation will give you the entire solution, but here the solution of this matrix equation is going to give you the next grid. This is the one next grid give. So for the next iteration, you have to use this as the I, again solve this matrix. So you have to keep on solving this matrix till you reach your TF. Fine. So then if you carefully see, for the problem you have chosen, this matrix equation will be looking like. So for the problem you have chosen here, so if you see for this problem, so this contains this, again this is going to be a sparse matrix because there is only 3 elements. Every row is going to contain only 3 elements, if you can see clearly, because that's what it given by here. This is the equation which I converted into a matrix form. So and what we are going to do is, you are going to find solve for u given this right hand side vector, that is this. You can see here I have actually rolled off the boundary points here. So which comes at this point will get rolled off here, sorry, here it gets rolled off to here. So and that's how this point comes here, and this is how we have construct the matrix equation. And you can see this is nothing but a simple tridiagonal matrix. Okay, so this is a tridiagonal matrix, and so this will eventually what you call, and you have to solve this tridiagonal matrix to find out the value of u for the next grid point. So every grid points, this matrix has to be solved. First you have to start with your initial value that is given here, and with the boundary values rolled off to other side, you solve for u of I plus 1, that will give you this time grid. And then after getting grid, then you keep solving, use this as your vector, right hand side vector, and solve for u of I plus 1. You have to keep on doing iterate this problem till you obtain your the u at certain x comma tf, for which you need to know the pair of the function at the time tf. and this is how an initial value problem is solved using implicit method. So compared to implicit method is more stable. It is just because every point what you're finding at I plus 1, they are not independent. They all, because since you're solving as a matrix equation corresponding to every matrix equation corresponding to every I plus 1 at grid, so all these points are somehow they are connected, and this eventually turns out that implicit schemes are more stable than explicit schemes, so one can trust the implicit scheme rather than the explicit scheme. But however, as I told you, solving partial differential equations is indeed very challenging. For any method you are using, you need to have a proper stability analysis. So how do you are going to do the stability analysis and all, I am not going to discuss in this lecture series. I will rather, the interested readers, you can go to the book given in the references and you can understand. So with this, I stop this lecture on solving the partial differential equations numerically, and that will be the end of the course on this introductory computational physics. And I thank you for your patience in listening all these lectures, and I believe this will be somehow useful in your future research career. Thank you.